Let's start with the most fundamental client-server model where you have a server that is exposing an API as a service and the client is sending a request to the API. But what exactly is an API? What does the request consist of and how does it even reach the server? Hi, I'm Pijush and in today's video we are going to talk about the beauty of the internet and how it works. So let's get started. Now we'll use the same client server model that we have seen before, and what we'll do now is we'll try to break the request down and form a data packet which is finally sent to the server. But before that, we need to identify the client and the server uniquely in the global scale of the internet, for which we use something called as the IP address. Now the IP address is assigned to both the client and the server, which uniquely identifies it across the internet, and the IP address that is assigned to a server is a public IP address using which the client can identify that, hey, this is the server that I want to connect to. But the IP address that is assigned to your home laptop or your mobile device, which is the client for the server, might not always have a public IP since it's connected to a home Wi-Fi router. So what happens is when your mobile device forwards a data packet through the internet to the server, your router will update the source IP address as a public IP address provided by your ISP probably, and then forward the packet. Cool. Now that we understand what IP addresses are, let's look at another address, which is a MAC address. Now, MAC address will uniquely identify a device in a local area network or in a particular network segment. So MAC addresses help identify a device in the local area network or in a local scale, while IP addresses help identify a server or a client in the global scale of the internet. Now, one thing to note is that the IP addresses are dynamic in nature and it changes for a server, while MAC addresses for a device is imprinted in the device itself. So you cannot change it unless you spoof it out. Cool. Let's now look at port numbers. Now the server that exposes an API has a process that is running in the server that actually exposes the API. Now to connect to a particular server, you must know the process and the port number identifies that particular process you want to connect to. And this port number and IP address pair is also called a socket. So when you're connecting to a particular server, you can say that I want to connect to a particular socket in a particular server, which is identified by the port number or the process identifier and the global destination, which is identified by the IP address. Cool. Now that we have seen what MAC address, port number, and IP addresses are, you might notice that we are not really concerned with the MAC address of the server. Since we don't really know that yet, it might be in a different continent itself, in a different network segment. Well, we are now ready to understand how the data packet is formed layer by layer. We'll start off with the application layer where your browser is running and you're trying to upload a profile picture to one of the social media sites, for example. So you need to transfer this data, which is your profile picture, to the social media server. Now for this, your application layer or your browser will form the data and will pass it onto the kernel to do the rest of the stuff. Now the kernel is the core of the operating system, and the first layer that your application layer sends the data to is the transport layer. Now the transport layer, what it will do is it will split the data into multiple parts. It will assign bunch of headers and it will form segments. Now the headers have source and destination port details or the port number of the process that you want to send this data to. Now the number of parts the data is splitted to in the transport layer depends on the maximum segment size or the MSS, which keeps on changing over time depending on the congestion in the network or the bandwidth. We'll look into the other responsibilities of the transport layer from flow control to congestion control later in this video. But for now, we can understand the main responsibility of the transport layer is to identify the process that you want to connect to, apart from flow control and congestion control. Now the transport layer will then send each segment to the network layer, which again splits them up, adds bunch of headers and form fragments. Now the headers in the network layer or the headers that gets added in the network layer has the source and the destination IP address to uniquely identify the server that you're connecting to. So the job of the network layer is to route the packets across the internet to help it reach the server, and it must have the destination IP added in order to facilitate that. Now the network layer will split the segments into multiple parts depending on the maximum transmission unit of the network protocol that we are using. For example, if we are using IPv4, it will have a different MTU than IPv6, We'll see bunch of network layer protocols in this video as well. Now, after this, each fragment is then sent to the last layer of the TCP IP stack, which is the data link layer or the network access layer. Now, the data link layer will again split each fragment into multiple parts, add bunch of headers, and form frames. Now, frames are the final data packet that gets transmitted through the physical medium to the next hop. So the main responsibility of the data link layer or the network access layer is to make sure that the data packet reaches the next hop, for which it must have the source and the destination MAC details in the data link layer headers as well. Interestingly, the size of each frame is different from the MTU in the network layer. The MTU or the maximum transmission unit in the network layer depends on the network layer protocol we are using, while the size of each frame depends on the physical medium through which we are actually sending the packet. For example, if we are using Ethernet, the frame sizes will be roughly around 1.5 bytes, while if we are using Wi-Fi as the transmission medium, the frame sizes can be around 2.5 bytes. And if we are using Jumbo Ethernet, the frame sizes can go up to 9 bytes as well. So just to understand for what we have discussed so far, the application layer formats the data and passes it onto the transport layer, which adds headers to understand what process we want to connect to the server, and it also has flow control and congestion control mechanisms, which we'll see later in the video. Then it passes it onto the transport layer, which adds headers to understand or uniquely identify a particular destination, in this case the server we want to connect to, and then the fragments are passed on to the data link layer, which adds bunch of headers to signify the next hop in the path to the server. Now, before we jump on to understand how the data packets are routed across the internet to reach the server, let's talk about latency. Now, when we talk about latency between the client and the server, we must also take into consideration the processing delay that happens in the client side for forming the data packet and the processing delay that happens on the server side to unwrap the data packet layer by layer. We are ready to now understand how the data packets are routed across the internet. We'll start with a local area network where you have a client and a server that are connected to a switch, and there are other clients as well. Now, each of the clients and servers have their own IP addresses and MAC numbers, and there are processes running in all of them, which can be identified by the port number. Now, say the client wants to send a request to the server, so it will create the data, format it, add bunch of headers, and create a data packet. Now, if you notice, we are identifying in the data packet that we want to connect to the process P1, the destination is IP3, and the next hop MAC address is M2, because the client knows that it connected to a switch, then the switch has a MAC address M2. So the client will now forward the packet using the physical medium to the switch. The switch will unwrap the packet and will see that, oh, well, I have to send it to a client or a server with IP as IP3. Now the switch doesn't really know about which MAC address this IP belongs to. And for this, the switch will need a routing table to understand which MAC address corresponds to this particular IP address, and then it can forward it to that particular device or particular server or client, whatever. Now, for this, the switch uses something called a address resolution protocol, and what it does it sends a bunch of address resolution protocol requests to all the clients and the servers. Each of them replies with their own IP and MAC addresses, and the switch creates a particular routing table. The switch can now use this to wrap the particular data packet with the corresponding MAC address of the server and can then forward it to the server. And there we have it. We understand now how a data communication in a local area network works. With that said, the clients and the servers in this local area network will probably have a local IP address assigned to it. What if the client wants to send a request to a public IP for a server probably in a different continent? In this case, the switch will probably be connected to a NAT enabled router, and what it does it whenever the client sends a packet to the internet, the NAT enabled router will update the source IP address with a public IP address, which is generally provided by your ISP, and will then forward the packet. So the NAT enabled router works as a proxy between the local area network and the internet. Now let's understand how the data packet actually flows through the internet. So before that, we need to understand what autonomous systems are. Now the entire internet is divided into multiple individual network segments called autonomous systems, which are nothing but bunch of routers interlinked with each other. And your client will be obviously part of one of them. Now there can be other autonomous systems designated here by AS1, AS2 and AS3. And say for example the server is connected to AS3 while your clients are in AS1. Now the clients over here knows about the server's IP address, but it doesn't really know which autonomous system it resides on or how to reach the server. For this, we'll look into a bunch of protocols that helps in routing packets and information across the autonomous systems and inside the autonomous system. The first protocol that we'll discuss is called Border Gateway Protocol, which is also an inter-domain protocol since it helps in sharing information across the autonomous systems. Now, in this protocol, every autonomous system has a designated router called the Border Gateway Router, which summarizes information of a particular autonomous system and shares it across to other autonomous systems. For example, over here, AS2 will communicate to AS1 that, hey, I can connect to autonomous system 3 as well. Now, this is a very simple description of what Border Gateway Protocol does, but this helps understand how autonomous system 1 can make decisions to route to autonomous system 3. With that said, we need to also find out that the server actually resides on autonomous system 3 because the clients only know about the IP address of the server. So we have figured out how autonomous system 1 can route to autonomous system 3. It knows about the path, but how to figure out that the server's IP resides on autonomous system 3? For this, we need to contact the internet routing registries. Across the world, there are multiple regional internet routing registries which has information provided by ISPs and other enterprises and has information of the IP addresses and autonomous systems. Now, this can actually help the autonomous systems or the routers in general decide on how to route the packets. You can also visit IRR.net to actually understand more about internet routing registries and packet forwarding in general. The clients can now send requests across autonomous systems to the server. We have discussed how autonomous systems actually shares information across autonomous systems using Border Gateway Protocol. And we have also looked into understanding how we can identify a particular autonomous system given a particular public IP. We need to now understand how does a router inside a particular autonomous systems makes routing decisions to route internally or to find a path to another router inside that particular autonomous system. How does it do that? For this, we need to understand intra-domain protocols. Now, intra-domain protocols helps routers inside a particular autonomous system create routing tables using which it can actually route packets internally. So let's look at intra-domain routing protocols. We'll actually discuss two intra-domain routing protocols with distance vector routing algorithm and link state routing algorithm. And let's start with distance vector routing algorithm. And the practical implementation for this is the routing information protocol, which actually implements this algorithm. Now, as the name suggests, distance vector routing enables a particular router to share its particular distance vector to its immediate neighbors. Now, the distance vector for a router will have the number of hops it has to make to reach any other router in that particular autonomous systems. Now, if you observe, distance vector routing algorithms doesn't share the entire topology of the graph. So none of the routers will have the entire idea of how the topology of the autonomous system looks like. Rather, it will use this distance vector to create a routing table using Bellman's-Ford algorithm. With that said, distance vector routing algorithms has a major drawback. It converges really slow if you add or delete a particular router from the autonomous system. Now, to solve this, we have a different algorithm called link state routing algorithms with the practical implementation called open shortest path first protocol. Now, in this protocol, a particular router doesn't just share the distance vector. What it does it shares its neighborhood information with all the nodes in that autonomous system. For example, router C in this particular autonomous system will create a packet with its neighborhood information and flood the entire network with this information. So whenever a particular router receives this packet, it will know that this packet is from router C, and router C is connected to router B, D, and E with distance as 1. Now I'm using the number of hops as the distance over here. You may use latency as a distance too. Now if you observe, each packet will have information from which router it's being sent, its neighborhood information, and a sequence number along with the cache TTL. Now the sequence number is used to prevent loops or cycles from happening. So if a router sees this packet again from this particular router with the same sequence number, it can discard it. Now the cache TTL is used to help a router understand till how much time this neighborhood information is valid. So every router will periodically share information or periodically flood the network, and at the end every router will have a global view of the entire network. Now this gives a router information of the entire topology of the autonomous system, and it can then use Dijkstra's algorithm to compute the routing table. Another interesting fact is that open shortest path first protocol doesn't really flood the entire network at once, since that may lead to network congestion as well. So what it does, it divides the autonomous system into multiple small segments, and each of the segments can summarize information and share across each other. Well, we'll discuss this algorithm in detail in a separate video where we discuss Dijkstra's shortest path algorithm along with other shortest path algorithms. Cool. Now, using this intra-domain protocols, every router finally has a routing table. For example, over here, we have a routing table for router A, which now knows that in order to reach a router E, it has to go to B first. We'll now look at all the layers that we have studied in this video and the protocols associated with it and the responsibilities of that layer as well. So we'll start with application layer, and as we discussed, application layer formats the data according to the particular protocol that we are using and then passes it on to the transport layer. Now the major application layer protocols are HTTP, which is used for defining APIs, and it is also used by your browser for fetching websites from servers. Second, you have domain name system, which is a set of rules and services that helps resolve a particular domain name to a particular IP. We'll see that in the next video as well. You have file transfer protocol, and we have discussed border gateway protocol as well. Now the transport layer has two major protocols. We'll discuss TCP or transmission control protocol first. Now this protocol creates a connection or a persistent connection with the server using a TCP handshake, which we'll look into it shortly in this video as well. And TCP ensures reliable and ordered delivery of the segments. Now TCP also has flow control mechanisms, and we'll see a TCP handshake in operation in this video as well. Now the second protocol in the transport layer is user datagram protocol, which is quite lightweight as it doesn't create any connection with the server. So it doesn't maintain any kind of a persistent connection with the server, and thus it's not that reliable as well. Unlike TCP, the server doesn't acknowledge any request from UDP data packets as well. Now, one interesting thing to note is that all the application layer protocols have their own port number as well, which is used by the transport layer to identify for what process this packet is supposed to be sent. Now, as mentioned earlier, TCP also has congestion control mechanisms which helps reduce or increase the segment size in the protocol based on the congestion in the network. Now, the transport layer will finally pass the data packet or the transport layer segments to the network layer, which has bunch of protocols for routing the packet across the internet and for network explorations as well. We have already discussed OSPF and RIP protocols while discussing distance vector routing and link state routing algorithms. And if you have ever used ping in your terminal for exploring or understanding if an IP exists, you have used ICMP as well. Now finally, the network layer will pass each fragment to the data link layer, which will form the final frame which get passed through the physical medium to the next hop. So the data link layer has various protocols for actually transmitting the data through the physical medium, and it depends on the physical medium it's using. So we have discussed one protocol in the data link layer, which is address resolution protocol, which helps identify or create a map for the IP address and the MAC address for switches. We'll now take a peek into the TCP handshake mechanism between a client and the server. So both the client and the server has to establish a connection between each other before sending a data packet. So the client initiates a SYN request with a particular sequence number. The server acknowledged that SYN request and the client acknowledged the server SYN request as well. Now this establishes a connection with a three-way handshake. Now, this handshake mechanisms are quite common in networking protocols, and that's one of the reasons I've showed this in this video. Now, if you notice, both the client and the server is also using a sequence number, which helps order packets as well. Now, the acknowledgement number from the client and the server's end indicates what is the next sequence number that I expect from your end. For example, over here, the server responds with an acknowledgement saying that the acknowledgement number is x plus 1. So once the data transfer phase begins, this client will send a data with sequence number as x plus 1, which the server will again acknowledge, and that's how the data transfer phase happens. Another interesting fact, if you observe, is that when the client is initiating a connection with the server by sending the first SYN request, the packet need not have any client data, as this is a transport layer protocol and this packet is to be consumed by the transport layer itself. Finally, after the data transfer phase, any party, the client or the server, can initiate a FIN request to gracefully close the connection with the server. Well, this brings us to the end of this video. In the next video, we'll discuss APIs, REST API, the drawbacks, WebSockets, how to scale your APIs, and briefly about load balancers and stateless services as well. If you like this video, do share with your friends and do subscribe to my channel. See you in the next video. Bye.